It's now my pleasure to introduce the second invited speaker of today's session, of this morning's session. Joachim Bungartz is Professor of Informatics and Mathematics at Technical University of Munich, where he holds the chair in scientific computing. He has also served as Dean of Informatics and TU Munich Graduate Dean. Prior to his current position, Dr. Bungartz was Associate Professor of Mathematics at University of Augsburg and Full Professor of Informatics at University of Stuttgart. Dr. Bungartz serves on many national and international review and advisory boards. He is chairman of the German National Research and Educational Network. He is a board member of the Leibniz Supercomputer Center. He's a steering committee member of the Council for Doctoral Education of the European University Association. Dr. Bungartz does research at the intersection of computational science and engineering, scientific computing, and supercomputing. He works on parallel numerical algorithms, hardware-aware numerics, high-dimensional problems, data analytics, and aspects of HPC software. His research is applied in applications such as computational fluid dynamics and plasma physics. Dr. Bungartz is a coordinator of the German Research Foundation Priority Program SPPEXA, Software for Exascale Computing. Please help me welcome Dr. Bungartz.
So thanks a lot, Edmund, for the nice introduction. It's my great pleasure and honor to be here with you today. I want to make 4 quite different points today. The first thing is a couple of remarks on where the performance comes from, so some fundamental remarks. And I want to present to you a nice funding scheme we have in Germany. Of course, funding is important. Then I will focus on education, give some examples for how HPC education can work in a maybe a bit unconventional scenario. And last but not least, I will give a couple of examples. I called it HPC software at work. So how algorithms can change the whole thing in a very manifold way. So you know this, that's a kind of the classical simulation cycle. And we also know these days that the things are not isolated anymore. It's not a cycle, it's more a graph. And if you want to do something for performance efficiency, you basically have to address all these kind of topics. This also gets visible when we have a look at where actually the challenges come from. So many of the challenges of today in HPC are related to, as I always say, one of these multi-notions. So some come along with modeling, multi-scale, multidisciplinary, multidimensional, multiphysics. Some come with the algorithms, multi-level. Some come with the data, multimodal data sources. And some come with the architectures, multi-architecture or multi-core. And this shows again that if you want to really change the things, you have to tackle all of these dimensions. So for performance, of course, algorithms are very essential. They are actually the essential. And if I'm speaking of algorithms, I mean a broad range of algorithms. So numerical schemes, discrete algorithms, but also newer ones to the HPC community, so data analytics, for example. If we look at a classical algorithm life cycle, it typically starts with a design, then comes kind of a more theoretical analysis, and comes a practical implementation. Finally, you tune it, you port it to different architectures. The first parts are typically part of what we call algorithm engineering. The second are part of what we call performance engineering. And again, if you want to obtain results, tackling one of these is not sufficient. You have to do performance engineering, you have to do tuning, but you have to do it with the best algorithms and not with anything lousy, which allows for an easy progress, maybe. So looking at the notions of efficiency we have, that's a very interesting part. So it started with the good old-fashioned Landau thing, so the order of n to the something, and today we have a much more manifold picture. So I believe that it's still not a bad idea to go for the classical complexity measure, to look for algorithms that have an optimal order of n to the something complexity. Nevertheless, there's this FLOPS performance measure, or how many % of the peak performance you obtain, which is, of course, a good hint if you do it for the best algorithms at node level and at system level. Then there's the memory and communication issue. Of course, being memory efficient is a good thing. Avoiding communication is also a good thing. Energy has come up as a topic, and it is, of course, obvious that we want to try to make our algorithms energy efficient. The The question is, and I would be very interested in starting some discussion there, actually I've not yet seen so many situations where trying for finding a cool solver, cool linear solver maybe, ends up at something completely different from if you try to really implement a fast solver. So there would be the maybe heretical questions. Is there a situation where slower might be maybe cooler or not? Then we have time to solution as a measure. That's of course also a reasonable thing, but one has to take care of when does the time to solution start and end. Typically you take only the computing time, but I think you should maybe more go for when does the problem specification begins and when ends the interpretation or the result you obtain. Something which would be very interested in including accuracy in a performance measure. For example, studying how many digits you obtain by a flop or by a giga or tera or whatever flop. This is also not that frequently done. And of course, the ultimate measure would be what kind of science do you get out from a kind of a computation. A very interesting view of or at efficiency comes if you look at what we call a cost-benefit ratio. So the general principle for numerical algorithms is you have a continuous problem, you have a solution, you design a discrete approximation, you create a discrete solution, and what you try to do is to make the error, some error, as small as possible. So now one can have a kind of an economic view at that cost-benefit perspective. What is the benefit? The benefit, of course, is the obtained accuracy. What is cost? So cost comes along in different appearances. The red cost here is the number of degrees of freedom you need to obtain a specific accuracy. And the blue cost is how many operations do you need afterwards to solve the discrete problems. You can extend this to more, but let's stay with the red and the blue for a moment. As we know, for example, for PDE-based problems, unfortunately, the red thing grows exponentially in D. So if you have an accuracy epsilon you aim at, if you have the number of degrees of freedom n, then this n is epsilon to the minus D, which is, of course, a big problem for higher dimensional topics. If you look at the blue thing, the typical situation is that we have something like a polynomial complexity. So depending on the solver you use, the blue complexity increases in the number of degrees of freedom. So this gives access to the starting points for improvement. The blue community, that's a solver community, they try to find optimal solvers that makes the blue thing as small as possible, typical linear complexity. And the red community, that's the discretization people, they try to make the discretization as appropriate as possible. For example, by using higher order elements, by introducing adaptive mesh refinement. This all is problem dependent. So it all starts whenever you have started your calculation. But there is also a problem independent thing. So can there be any a priori grid structure? Can there be any grid structure which is optimum independent of the concrete problem? And I'll come to that back at the end when I have my concrete examples. What is also discussed in the context of performance is, of course, kind of a co-design. So I believe that co-design is important, but only if it's done in the right way. And I mean the right way is kind of an inclusive or an holistic way. So it has to include the underlying algorithmic core, which means we need a co-design between algorithms and applications, and we need a co-design between algorithms and machines. If you leave the algorithms out, if you do a classical co-design as it is still frequently done between applications and systems, there's the risk that you just take into account applications that do not have the best algorithm core. And then you optimize in a direction which is probably not kind of an optimization direction you would like to see. Or, for example, if you have a 100 hours run with a code going for 80% peak performance, a lot of people are happy because they say 80% peak performance, that's great. Of course, it's great. But if you can obtain the same result, the same scientific result, with another code running for 10 hours, with only 8% of the peak performance, but solving the same problem nevertheless in 10 hours, there's a big question. What is the performance measure that we would like to go for? And I have two examples that this inclusive or holistic way I really think is important. The first is think of all the multi-level algorithms we have. This was kind of a new algorithmic pattern, end of the 70s, beginning of the 80s. At the beginning and still now, it is not in that many application codes that it could be. But nevertheless, we should take this kind of optimum algorithmic scheme if we go for optimizations. We do not want to see these tons of parallel results for Jacobi iteration or whatever, but we really have to do our optimization on the best algorithmic solutions available. And a second example is if you look for the multidimensional issue, which is very important, for example, if you go for statistics, if you go for big data, but also if you go for computational finance. The majority of high-dimensional things are still done by Monte Carlo. So if we now take one of these applications and do an application system co-design, this makes the co-design in an algorithmically very suboptimal direction. So again, I would say don't go for the lame ducks, but find new stuff and do the optimization in that direction. Okay, second part, funding. In Germany, we have this, what we call a strategic national priority program, SPPEXA, Software for Exascale Computing. And this is now also a multinational thing because we managed to get it synchronized with a call in France and a call in Japan. So it fosters fundamental research and wants to establish collaborative interdisciplinary co-design between applications and methods, so algorithms. It has been quite a long way to convince people. First idea started in 2006. We got it finally started in 2013 with 2-3-year funding phases. So the research is driven by the domain sciences, by the applications, but it is powered by scientific computing, by informatics, so by computational science methodology. In some parts, it is more evolutionary, so improving existing things. In some parts, it is disruptive or revolutionary, thinking about completely new approaches to problems we have. And there is this international component now, as I mentioned. So we have 6 core research directions which we have identified as being crucial if we want to go for progress in software for exascale computing. That's algorithms, programming, application software, system software, software tools, and data management. So currently there are 17 interdisciplinary research consortia funded. Each contains 2 to 5 groups and has to address at least 2 out of these 6 topics, because we really do not want to go in an isolated monodimensional way, but we want to connect things. And in the second phase, we have now this strong international flavor with French and Japanese collaboration parties. So currently more than 50% of our projects are international ones, and more than 50 universities and institutions worldwide are involved. If you look at the funding, the number is astonishingly small. So the program gets 4 million euros per year for 6 years. So if you look at it in a positive way, you can say, oh, what kind of a huge leverage for that money. If you look at it at a negative way, you could say that's peanuts compared to what other countries do. But we have that, actually, I think for DFT, it's not but probably one of the first times that we really have an international endeavor now involving not only French, Japanese, but also partners from other countries. Okay, this is some people you might meet, many of them here, of course. We have a lot of dissemination activities, so we organize and fund a lot of workshops to really bring what we are doing into the scientific communities, and this happens also at a global scale, of course. Of course, if you look at the funding landscape in Germany or even larger in Europe, there is more than this one program, SPPEXA. So the DFT, the German Research Foundation, for example, has launched 2 nice, but unfortunately a bit small, specific calls on sustainability of scientific software and performance engineering, which I think are both very important topics and which are typical topics that cannot be funded in many of the classical science tracks, where you look for a very concrete scientific result and not that much in that how can we put software at a more sustainable level. Then we have the Federal Ministry, who had a high-performance computing software program, 5 following calls. Then we have the federal government and the states, who are currently investing a lot in establishing a national HPC infrastructure, so leaving the HPC from the project base into a more institutional funding, and also leaving this perspective of being focused on the racks only and having a total cost of ownership strategy. And of course, if you have a bit insight into the German landscape, everything is currently focused on this excellence strategy again, where every university tries to get this kind of a label to be really, really excellent. And of course, there we expect also high-performance computing activities being involved. And also at the European Union side, there are a lot of funding channels, some addressing more real scientific projects and some addressing more infrastructure. And for example, this European Exascale Software Initiative is a nice project that tries to prepare the landscape for future exascale systems. So education, and that's really something where I think one has to invest a lot because educating high-performance computing is not that easy within the existing education patterns. That's why I think it has to be done at all levels. So we have to enhance the classical programs, we have to enhance informatics, we have to enhance engineering and physics programs. What is a physics program without a very strong computational physics component these days? But also through specific programs at my university, for example, we have a computational science and engineering, a computational mechanics, data engineering and analytics, games engineering, a bioinformatics program, and all these programs are, of course, relying on high-performance computing capabilities of the graduates they produce. But also we have to think about single courses. Are there chances for designing new courses that maybe transport this kind of an interdisciplinary education better than just doing the normal thing and telling people that they should do it in an interdisciplinary way? And of course, we also have to leave the classroom. And I will give you a couple of examples where we are really leaving the classroom for doing maybe a bit better university education. That this is relevant, I think there's a very nice study that has been funded by SIAM, the CSE branch, and the European Exascale Software Initiative. It came out from a workshop in 2014 in Breckenridge. And if you look at the two graphs, the nice result was, okay, we have Moore's law, we have the progress of the machines, but we also have a similar algorithm progress if you look at linear solvers, for example, starting from Gaussian elimination and ending up where we are today. And if you look at the right side, there is also an increase in model complexity. So starting from a simple PDE, and nowadays you have uncertainty quantification, you have data-centered simulations, and so on, inverse problems. So also the models have become more complex. And this shows again, if you really go for an improvement in efficiency and performance, you have to go for the models, the algorithms, and of course, the usage of the machines. And this is the complicated thing for education. So one first thing we made, we introduced a course, kind of an interdisciplinary NAP for turbulent flow simulation on HPC systems. So two groups from two different programs, from mechanical engineering, bringing in the physical, the flow, and a bit of numerical expertise, and computer science people bringing in a bit of numerical expertise, and of course the parallel programming expertise, and putting them together in one lab course, including experiments that everyone gets an idea what the flow problem really is, including some information on the model, and then including implementing a solver and putting it via MPI on a parallel machine. This was a fascinating experience for the students because they, for the first time, really realized what the contribution of the others can be, but also what their own contribution in such kind of an endeavor can be. So that's now an example of just one specific course that has been implemented in a couple of programs, which really transports this interdisciplinary idea. Or in an honors program, we have this what we call a software project to increase the software capabilities of our computational and high-performance people, because I still believe that despite all the activities that occur, the software engineering professionalism and the high-performance computing professionalism is still a bit apart, and this especially holds for university education. So what we make here, we get teams of 6 to 9 students and tell them, okay, now you are a small software company. There's a customer from industry who wants a simulation code, and your task is do this simulation code from scratch. In 9 months, the customer will come and he will tell you whether he or she is happy or not. So the task is deal with the complete software system from the design until you hand it over to the customer. And the goal is, of course, less the final product. We do not want to have really competitive solvers at the end. What we want that the students learn how this process works in software engineering. And you'll see on the bottom left side a couple of topics. So we have really a broad range of topics, a broad range of customers to really bring this software engineering spirit a bit into the computational and high-performance computing group. Then we have Ferienakademie. Ferienakademie is kind of a summer school. 3 universities have organized for more than 30 years now. There are different courses. And what I have been offering for the last couple of years was a course, Let's Play Simulated Physics for Interactive Games. So we want to let them produce a game. Okay, that always increases the motivation. But a game which is simulation-based and a game where the performance in programming plays an important role. So the setting was students decided to go for a 2-player boat race. So there's flow, there are rigid bodies, there's coupling of flow and rigid bodies. They have to use a game physics engine. There's interaction via Kinect. So everything was very Scrum and very agile, of course. And at the end of the 10 days, we expected students to provide a game. Okay, that was really a new experience of peak performance if students were sitting on the peak of a mountain and going for efficient programming. And that's here the kind of the result. So, this was not the thing I wanted to do. That's what I wanted to do. Okay, I don't claim that this is a state-of-the-art computer game you could put on the market. But I think that's a very nice thing for 10 days, undergraduate students who started really from scratch. It is an interactive game. It has a physical background behind, so that's kind of a thing where I also think you can nicely let students train on performance. My fourth example is a doctoral retreat. We also have a similar format in this SPPEXA program that we send our doctoral students for 1 to 2 weeks on a retreat to get some kind of a team coding spirit. And this turned out to be extremely helpful even at the doctoral level, because still you have the situation, even if you have an HPC program, you still have the situation that some people come from mathematics, some people come from physics, some come from informatics, and they do not have the same level of understanding what high-performance computing actually means. And my last example is a bit like taking coal to Manchester. So this is an example which happens here at this conference and which I think is a really formidable thing. So my university started in 2015 in Austin for the first time to send a student team to the student cluster competition with a great name, Too Much Fun. We had last year a team, and this year we have a joint Bavarian team from Erlangen and Munich. And I think this student cluster competition is really an excellent format, and it deserves all kind of support from the supercomputing community. Because these people we see there, sitting there programming days long, night long, that's the future of supercomputing. So that's really something some point I would like to make. We also made the experience that by such a thing, it is possible to attract really the most brilliant of our students to high-performance computing. So at least that's kind of maybe it's only a German phenomenon, but actually I don't believe that. But if you look at where the brightest of our brains typically go in, that's not that easy to attract them to high-performance computing, because there are a lot of other attractive, intellectually attractive subfields in supercomputing. And by that, we got some of the really brightest people into our team. It produces a huge motivation and, of course, also a huge gain of experience. So that's the future of supercomputing, so let it grow. I'm very happy that this year we have 16 teams. So I'm looking forward to taking this student cluster competition even a bigger share of the exhibition area. Okay, the fourth part now going a bit into research, into some examples on high-performance computing software, and I want to show you how algorithms can improve the situation and how multifaceted the understanding of algorithms there can be. So my first example is from a numerical perspective, a very classical one. You have a numerical core problem, an eigenvalue problem, which turns out to be a bottleneck. The application scenario was an electron structure code. We were in discussion with computational chemists. And the issue was that there was a very early end of scalability for all their kind of symmetric eigenvalue solvers they had. So what we decided then is that we founded some project consortia, interdisciplinary, with people from mathematics, from informatics, from chemistry, and from high-performance computing centers. And we actually took up at that time, not that new, but a bit sleeping, algorithmic idea to have a two-step tridiagonalization and trying to get the best out of this when going on the different parallel machines. What came out as a result is, of course, first we got a huge gain, I will show that, by algorithm improvement for this code, but it also occurred that a complete library for eigenvalue problems called ELPA came out of that, which has currently very high access rates. For example, it's now public domain. So the idea was to make this transformation to diagonal form, which frequently occurs in these eigenvalue algorithms, to do this in two steps, first to bend it and then to diagonal form, because this opens the way for BLAS-free algorithms, and this, of course, increases the efficiency of parallelization. There are a couple of new algorithmic ideas, generalization ideas we currently have, so going for general eigenvalue problems or introducing some auto-tuning that, depending on the machine and depending on the problem, depending on the matrix size, the code could maybe decide itself what kind of variant is the best one for doing the simulations. These were our early results, which at that time were done on Int'l Sandy Bridge, which showed that the scalability by introducing this algorithmic pattern of the existing software could be tremendously increased. And this is a bit more recent thing where the code has now been ported to KNL. So first, when the system was not yet available, we did it on an emulated hardware. Then Int'l provided to the Max Planck Computing Center a one-node test system, and then this was ported to ANL's theta system. And we have now runs up to a matrix size of 1 million on 200,000 cores with a nice scaling behavior. And this is actually one of the largest eigenvalue problems that have been tackled, at least what we could find in literature. So that's a classical numerical part. So now Monty Python would say now for something completely different. But numerics is not everything. So another big algorithmic issue is how can we bring more dynamics in scheduling? Many of the HPC applications these days are adaptive. They are dynamic. But the slot allocation is typically that you get a fixed number of cores for a fixed amount of time. But that's not what you need. At some points, you need less. At some points, you need more. So how can we make the scheduling, the research allocation more dynamic? And this is an idea called invasion, and it is followed in a collaborative research center we have between the universities of Karlsruhe, Erlangen, and Munich in Germany. And this mainly has a focus on embedded systems, but looking at the complete stack, hardware, operating system, languages, compilers, up to applications. Our task in this program is to look at what this invasion idea can help in high-performance computing. And for that, we created an IOpenMP and an IMPI, so an invasive OpenMP and an invasive MPI, which shall help to, in an example way, to implement this invasion idea in our current dominating parallel programming models. So what you see on the lower left side, for example, is now an already older simulation, we took a 40-core machine with this IOpenMP, and we took several Tsunami simulations, one after the other or in parallel. And now we compared what OpenMP did if they just do one Tsunami after the other, let OpenMP do the parallelization with all these optimization flags, and then count the time. Then we used thread building blocks, that's the green thing, and the blue thing is our invasion thing, that we really let the different Tsunami runs compete. So if one needs more, he steals the cores. If one needs less currently, this solution, this simulation gives free a couple of cores. And by this, we can obtain, as you see here, almost a factor of 50% in efficiency. This was now extended to MPI, so we did this IMPI, this invasive MPI. Our example was again Tsunami. So why Tsunami? Because the Tsunami simulation is obviously something where you have a very adaptive and a very dynamic change of the need for compute resources. So at the beginning, you don't need anything. Then, for example, you have a sequake. Then there's some point where this starts. You need a high resolution there. And then when the wave propagates, you have to increase resolution where the peak of the wave currently is. And behind the wave, maybe you can already again reduce the computation because you cannot resolve the whole ocean in a fine way. So that makes clear that this is kind of an ideal application to show what this kind of a dynamic scheduling could bring in terms of benefits. Of course, there are benefits for the individual application. Shorter queuing time, you can just get access, even if there's only one or two cores or nodes are free, your program can already start. And of course, there's an improved resource efficiency, and you see this on this picture on the right. So the red thing is something which was done in the classical way, a fixed allocation, let the thing run, and stop the fixed allocation, reduce it to 0 when the simulation is done. And the blue thing is our invasive thing. Start only with a few nodes, let the number of nodes increase or decrease as it is needed, and again stop when all the simulation is done. And what you see, the overall computing time was not improved. So it took a bit longer, but if you form the integral, you see that if you count the CPU hours over all the cores, then we got almost a reduction to 50%, which means the overall usage of processors was reduced to almost 50%, which is, of course, a gain. Of course, if you have an application where you need a fixed point of time where it is done, then you have to do it in a different way. But it can improve the situation. And the benefit for HPC systems, so from a center perspective, of course, is that much more can be done within a specific time frame. You avoid these idling cores because the application who has been given the cores has no usage for them currently, and they cannot be assigned to another application. And it also can help to stabilize the overall power consumption because you have a much better control on how many cores, how many nodes are really working currently. Yeah, maybe I have to do this that way. Yeah, here you see now this invasive MPI thing. We start with only one node, and at the end of the day, we have 4 nodes with 16 MPI ranks. So this example has been chosen deliberately small, just to demonstrate that we can now work with MPI and with the allocation of nodes and cores and ranks in a very dynamic and in a way that really fulfills the needs of the application. Third thing, again, something completely different. What are the challenges here? The challenges here are multidimensionality, and we want to get access to a nice scheme that enables algorithm-based fault tolerance. And we want to do this by going for this a priori grid structure I mentioned at the beginning. So what is a priori grid structure? This means introducing a grid structure that is better for many problems, independent of the specific problem. And my example is, probably you all know this game, a battleship, so where you have to shoot in different fields, and you hope that you hit the ships of the enemy where you don't know the position of. So when you start now your first shot, you probably would not do it in A1 or something like this. But one strategy could be to place the first shot in a way that you reduce the space where a ship can hide as much as possible. And here you can do by one shot, you reduce the area by a factor of 50%. Now, if you have 4 more shots or 4 more grid points, what would be now your strategy to shoot? Hopefully not the left-hand side. Because if you do it on the left-hand side, you don't get any reduction in the area where a ship can hide. Whereas if you do the arrangement of shots and grid points as I do it on the right-hand side, you get another 50%. And this shows you, independent of ship size and independent of the strategy of the opponent, there's a clear thing you can improve by placing your shots, or in terms of a discretization, by placing your grid points. Okay, mathematically, this is a bit more complicated, but a very similar idea leads to what we call sparse grids, where you can almost overcome this curse of dimension, and the grid pattern you see here, that are the typical shape of grids that come out, and that are very similar to this pattern I've just shown you. So how can we get access to sparse grids? Because you do not want to program everything from scratch. So there's a very nice idea. The sparse grid on the left-hand side can be interpreted as a superposition of several coarse full grids. So what you do with grids, you can also do with solutions. So why not take your standard code, solve your problem on these regular grids, and then combine at the solutions to get a sparse grid solution. There are a lot of issues because we have this second level of parallelism. These different problems are completely independent. You only need synchronization for the combination part, but the simulations can be done completely in parallel. Just to show you some numbers, if you look at the 10-dimensional problem at the resolution level 12, the full grid would need 10 to the 37 grid points, the sparse grid 10 to the 12, and this combination approach 10 to the 14, which is actually feasible. So we are applying this now for a real physical problem for plasma physics. Why plasma physics? 2 reasons. The first reason is this is 5-dimensional, the Vlasov equations, and that's great. 5-dimensional is already an area where you would not like to invent 5-dimensional tetrahedra and to refine them. So classical approaches here typically are not feasible. And we have a code. We have this code Gene, which is a fairly successful high-performance computing proven code for doing this kind of simulation. And what we now do is that we let this code Gene run on all of these subgrids and make the combination, and then we get a sparse grid solution with all the beneficials out of this computation. But by only running the simulation on standard grids. So there are a lot of benefits. The one benefit I would like to focus on, and this was also presented by Michael Obersteiner in his talk at the workshop and on Monday, is this opens a very nice access to algorithm-based fault tolerance. Well, what if a core fails? What if some of these sub-calculations fail? We don't make checkpointing, we don't make restart, we don't recompute again, we just skip it and we look for a detour. We take other grids, as indicated at the bottom, and then we make another combination. And these other grids are very cheap because they are very coarse. So this, I will show you just in a second kind of performance results. So we have here a situation that the algorithm itself can find a detour without that you have to stop or to recompute anything. So what about accuracy? The upper right thing, that's a classical picture norm we are so fond of. So what you can see is you have the original calculation, you have the calculation with faults, and after recovery looks very similar to the original thing. And this can also be quantified if you look at the graphs. For example, at the left, in the graph on the left side, the dots stand for 25 and 50% faults. And even, I think, the most pessimistic among you would not expect 50% faults on an exascale system in one single run. So, and even with these 50% faults we can recover this by the application itself, still in a way that we basically do not see a big change in the error. So the error increase actually is in a couple of several percent, so it's not a big deal. And on the other hand, here in the upper right graph, if you look at the purple thing, this shows the cost for recovery, so this can basically be neglected. So we have a nice scalability. It's not disturbed by our recovery scheme, and we have a recovery which comes extremely cheap and which is extremely effectful. And last point on that, this is also a nice access to silent data corruption, so algorithmic detection of that. Because we basically solve the same problem of similar grids. So if one of these grids goes wrong, if one of the cores goes wrong, we can see whether the result looks completely different than it looks on the other grids. And we can identify with a high probability, this is probably a faulty thing. So let's take it out and let's treat it in the way as I just described it. OK, the last example, I will skip that more or less, is some molecular dynamics where we really go for very large particle numbers. So actually, to our knowledge, we did one of the largest particle numbers, 4 times 10 to the 12 in 2013, got the Brace ISC award of that, and we are currently, again, working on that. And let me just close with a movie. So why do you go for that many particles? Because our application is process engineering. It is not material science. It is not life science. It is a chemical reactor. And the chemical companies want to improve the performance of their chemical reactions. And that's why we need to study things like droplet formation, nucleation over a longer period of time. And for that, we need large particle numbers, and we need relatively long time steps. And that's why we also invest in that. OK, I hope the message arrived. 4 points. Performance and efficiency are multifaceted. Funding is crucial, so go for innovative schemes. Education stays important, and in science, algorithms can make a very big difference. So this is my acknowledgement slide. I'm sure I forgot some people. Sorry about that. As I write on the bottom line, it will probably happen again next time, but I hope with other people then. Thank you for your attention.
We have a little bit of time for questions. Please come up to the microphone if you have a question. Maybe I can start with, there's a question at number 3.
So as an ex-alumnus of the Technical University of Munich, I have to say I'm really impressed. First, that you dared to use Latin in the title of your talk. Second, that you were able to actually compete with one of your student groups with the Oktoberfest. That's a real challenge. And then third, because you actually brought to light one of the dirty secrets of high-performance computing. And the dirty secret is that high efficiency in terms of flops versus peak doesn't absolutely not mean you're using a good algorithm. You had one of those examples, and I think that is really enlightening. So the question I have is that a lot of examples you've shown here show groups working together with a kind of mathematical background. What about bringing into the game groups who typically have 0 or close to 0 mathematical backgrounds? Thinking about the medical science, I can also think about social science, psychology. That's a question.
Well, this has to happen, and it will happen. We are just currently in maybe a fortunate situation that our standard fields of application typically come from the classical STEM. So they come from engineering and physics group. But of course, I think there is also there are a lot of things going on, especially in computational medicine. Humanities or social sciences are probably more interested in the data analytics part than in the simulation part, but this will also follow. And concerning the Latin language, well, I believe in innovative languages.
All right, let's stop here, and let's help please help me thank Hans Joachim Bungartz again for his talk.